So in this video, we'd like to look at the properties of a characteristic polynomial of a matrix M of size n by n. And by definition, characteristic polynomial is the determinant of the n by n matrix lambda times identity minus m. And if you look at the determinant formula and expand it, we can actually get a polynomial in lambda as the variable of degree n. And now, let's go deeper than that. Let's say you're able to factorize the polynomial of degree n into this way. And the fact is that if you make this determinant 0, you can easily get the eigenvalues, which are basically lambda 1 up to lambda k, right? And please look at the number of times the lambda 1 is repeated. Some people use the word multiplicity for that. And if we try to determine the eigenspace correspond to each eigenvalue, the fact is that each eigenvalue should have the eigenspace at most the same as a multiplicity, which is n1 for the first eigenvalue. And similarly, the same theory applies to each eigenvalue, which means, for example, for the last one, the dimension of the eigenspace is going to be at most n subscript k, right? And let's look at a simple example now. So please look at my current problem now. I'm not giving you the matrix M. I'm just giving you the fact that the characteristic polynomial of this matrix is going to be something like this. And can you tell me some information about the matrix M? For example, can you tell me the size of M? So you see, please look at the degree of this polynomial. This one is going to be degree 6, right? Degree 6 because you see lambda is multiplied 3 times, and then lambda should be multiplied to 2 times, and there's one more copy of lambda. So if you multiply all these lambdas together, you would get the highest power term, which is lambda to the power 6. It gives you a sense that M should be a square matrix of size 6 by 6. And let's look at the second problem. So are you able to find all the eigenvalues of the matrix M? And basically, it means we have to set the characteristic polynomial be 0, and you can solve for it. And fortunately, we have all the factors already. So basically, there are only 3 different eigenvalues for the matrix M. And you see the multiplicity of 2 is repeated 2 times, and the last eigenvalue 3 is actually repeated 3 times, right? So now let's look at the last part of this problem. I would like to ask you the dimension of the eigenspace corresponding to each eigenvalue. Please look at the multiplicity of each root of the characteristic polynomial. For example, for the first eigenvalue 1 is not repeated, right? So we know that in that case, the dimension of the eigenspace is exactly 1. But for the second one, because the eigenvalue 2 is repeated 2 times, and there's some uncertainty here. So the dimension of the eigenspace can be 1 or 2. We don't know. We don't know. It depends on the matrix. And for the last one, because the eigenvalue 3 is repeated 3 times in the polynomial, so basically it means at most the dimension of the eigenspace is 3, but it can be less. We don't know. It's something you need to solve depending on the matrix M. And basically, that's the answer to this problem.